Yes, thank you. Okay, so this talk is very definitely not for the twisted graphene people. I hope they'll help me out if I get stuck by difficult questions. I think I might, actually. But thanks to the rest of you for coming. And my goal is to try and tell you why we're here this week. The original title of my talk I wrote over here, Chicken Wire Bingo. I'm not sure if that's an obvious sounding title for a talk, but the original title was actually Chicken Shit Bingo, which I...
You did not give me that option.
No, wouldn't it have been okay? Chicken Shit Bingo, if everybody in Austin knows what Chicken Shit Bingo is. Chicken Shit Bingo is a relic of what is referred to in Austin as Old Austin, which is the Austin of the movie Slackers. It's a cultural relic that characterizes the values of Austin in the 70s and 80s, which can be characterized by the words, let's say, enthusiastic pointlessness. But Chicken Shit Bingo remains as a Sunday afternoon pastime, and I am actually, and this is probably why this title resonates so well with me, I am a winner of Chicken Shit Bingo. And for Chicken Shit Bingo, well, the chicken shit is just what it sounds like it is. If you get bored with my talk, you can Google it. Bingo is what you yell out when you win any kind of bingo, including Chicken Shit Bingo. But this title also sort of describes what we're doing here this week. This is a workshop about a very surprising experimental discovery in the world of two-dimensional materials, and that is the world of chicken wires. Okay, so this is a chicken wire. It's a regular grid that keeps chickens where they're supposed to be, I guess, and it's not a terrible representation of a two-dimensional material. So the two-dimensional materials were first, of course, have been around forever. Very anisotropic materials with strong chemical bonds within layers and very weak interactions between layers. But starting around 15 years ago, with the work of Andrei Geim and Kostya Novoselov on graphene sheets, people started to develop techniques where they could really isolate initially just one sheet of two-dimensional material and measure the properties of that semi-isolated system, the electrical properties, optical properties, etc. So this is like a two-dimensional material, and they can be isolated almost as well as this. So you can imagine this as a square lattice of some kind of atom that is very weakly coupled to other lattices. And one thing that these kinds of grids, of course, are used to diffract light of the appropriate wavelength. And so let me just mention one property. I'm going to define something which let me call the transmission or the transparency of the grating, which is a function of position, and basically that grating is transparent except where the wires are. And so this, if the grating were perfect, then the transmission stays the same if you translate by some integer number of steps of the grating, some integer number of lattice constants. And that means that if I do an expansion of this, a Fourier expansion of this, then all of the functions that vary in space have to be periodic with this periodicity, and that means that if I do an expansion, then I only have non-zero coefficients for those wave vectors which correspond to an integer number of wavelengths in one period of a grating. So this is an example of the periodicity that we have in what, when I learned it, was called solid-state physics. Of course, this is the tremendous simplification of everything in solid-state physics. I think that your group is not interested in simple things. So, okay.
So I assume you're meant to write y in the equation and then r.
Y hat.
Yeah, thank you. Nice to see you, Marty. Okay, so this is the starting point, as you all know, for the theory of the electronic properties of a solid, at least if we ignore interactions. Let's say I have an electron wave moving in a potential, and instead of the potential has some periodicity, like it does in a perfect crystal, then in that case, if I wanted to calculate matrix elements, write down the Hamiltonian, for example, in a representation of free particle states. You were going to say something?
Allan, if you want to be as picky as he was, that A should be replaced by R.
Yes, thank you. Thank you.
1 and 2 by NX and Y.
These don't have to be the same. I'm okay. Okay. Which free particle states are coupled together in a crystal? I think all of you know this as the theory of nearly free electrons in crystals. And if I so if I put a periodic potential and calculate the coupling between momentum eigenstates with plane wave functions, then what you can easily conclude is that such a potential only couples together states that are separated by one of these quantized wave vectors. And this set of quantized wave vectors is also a lattice and is referred to as the reciprocal lattice. And so wave vectors are only coupled, momentum eigenstates are only coupled together if they're separated by some reciprocal lattice vector, some quantized wave vector. That means if I define a elementary area, and this is 2 dimensions, that means I can define an area in 2 dimensions where no momentum eigenstate, free particle state inside this area is coupled to any momentum eigenstate inside this area. In other words, momentum modulo reciprocal lattice vector is a good quantum number. And that means that if I have an electron wave in a crystal, it's almost as simple as a particle in free space. It's labeled by, we have states labeled by a momentum. It's a so-called crystal momentum, a momentum that's inside this finite region of momentum state. and the energies depend on momentum. The only thing that's different from free particles is the dependence of energy on momentum might change from free particle form, does change from free particle form, and we might have many states for any given momentum. Okay? So let's say, for example, if I just plot in one direction, energy as a function of momentum in the Brouin zone, let's say with just along the x direction with ky equals 0, I can get some set of eigenstates, and it can happen, very often does happen, that the relevant states in a crystal are more or less slightly distorted atomic states, and then the energy might not depend very much on momentum, and that state, that group of states, that band of states, may be well separated from other states. Okay, so this is basically, reminding you of a early lesson in a solid-state physics textbook. This is the complete solution to the quantum problems for electrons. Would be the complete solution if the electrons didn't interact, in which case this subject would have, finished in 1940. So this is actually the theory of non-interacting electrons. Okay? And this is more or less the theory of electrons in a sheet of carbon atoms, a graphene sheet, a single sheet of graphene atoms. It turns out that there's one type of atomic orbital, the actual atomic orbitals that are odd in the plane of the graphene sheet, and those are the ones that are important for most of the transport properties because they're near the Fermi level that separates occupied and empty states. And interactions in a graphene sheet don't play a very central role. Okay? But there are other systems that are common and in which interactions play a very central role. And then the most important term in the quantum mechanics, the Hamiltonian that describes the quantum properties, in the case of strongly interacting electrons, is the interaction term. And in the very simplest case, where there's only one type of atomic orbital, one band of relevance, we can describe this interaction in a very simple way. This is a Hubbard model for a single band. That means the states are labeled just by a site index I. Two particles particles don't interact with themselves, so if I only have a spin degree of freedom on each site, then only if the two particles, the only way I can have two particles to interact with on the same site is if those two particles have the same spin. Okay? So the interaction Hamiltonian is diagonal in real space. In this case, it's discrete real space because I'm imagining there's only one atomic orbital available per site. Whereas the kinetic energy term modified by some potential in a crystal is diagonal in momentum space. And if we just had this term, it's easy to say what are the quantum states of the system. And so, for example, there's a special state which has, in the case of one electron per lattice site, there's a special state where I just put one electron on every site. And that state completely avoids this repulsive interaction energy and has a low energy. That state is actually, in order to localize a electron wave on one site, then you have to, as you can imagine from the uncertainty principle, average over all the momentum states. And so that means that state, if I have a half-filled band, in order to optimize the interaction energy, I have to basically occupy all momenta, in which case I can't take advantage of the possibility of basically what is chemical bonding, putting the electrons in these states with the optimal wave vectors. And so there's a competition between these two. And when they're both roughly the same size, we're not very good at understanding what happens. But there is a very famous example in the history of solid state or condensed matter physics, which is where we have electrons described which are more or less in a single type of atomic orbital. And they have a dependence of energy on momentum, a so-called energy band term. Each of these groups of states with particular dependence of energy and momentum is called a band. And the characteristic energy of non-interacting electrons is the width of the band. And they have the property that the width of the band and the interaction are comparable. And then what happens, we know from many, many tens of thousands of papers in the scientific literature, these are very special materials because they're the highest temperature superconductors of all materials. And superconductivity, if we want to do, if you're a fan of quantum solid state physics, superconductivity is just about the coolest thing that happens. So we like superconductors. And these materials are the best superconductors. And they have the property that when they have close to one electron per atom, they form a state like this. They minimize the interaction energy. They avoid putting electrons on nearby sites. This state is an electrical insulator, as you can imagine, because the states are stuck on sites. But it turns out that if you take some of those electrons away, that's when you get the high temperature superconductivity. And really having a predictive understanding of those materials, those which are unique as far as we've discovered so far in all of nature, has been a tremendous challenge for the field. Much is understood, but perhaps maybe even the most essential things are not understood. Okay?
Unless you're plotting doping on the x-axis.
Let's say that again.
Plotting doping on the x-axis.
Yeah, so this is number of electrons times the area of a unit cell. Let's say the number of electrons per atom, per carbon atom in this case.
False.
And what else? And this is T. And this is a magnetic state. It actually turns out, as everybody, mostly people in the room know, an antiferromagnetic state. And this is the magic state we're so proud of, the superconducting state. Okay? Okay, so that's just solid state physics. And so that now now I come to bingo, okay? So this is chicken wire, and now I come to bingo. The people responsible for the bingo in this field are the experimentalists. In the first place, Pablo. Is Pablo back from lunch? Yes. Pablo's right there, okay. So what Pablo discovered was that something very special happens when you put two chicken wires, one on top of another. And here we have the world's most poorly designed demonstration, designed by me after Andrea told me last week that I should give a Blackboard talk, and I knew I needed a prop. And this design has two problems. There's two chicken wires on top of each other. First of all, that part's okay. This wire is not chicken wire exactly. Chicken wire is usually a honeycomb pattern, not a square lattice. And it's usually finer. And I realized that the real chicken wire would be, after consulting one of the clerks at Lowe's, actually, I concluded that the real chicken wire was going to be too fine for my demonstration, but I did not go up granularly enough. So I'm going to have to ask you to really try and help me here. But what I'm going to hopefully show you physically here, and which you probably are already aware of, that if I have two grids and rotate relative to one relative to the other, I make a long distance period that, and the periodicity is inversely related to the twist angle. So, David, you're a good experimenter, so look hard. Tell me something happens. Did something happen? You can see something? Okay, let me turn it around. Okay, it works a little bit. Next model will have thicker wires still. This is also industrial strength. Otherwise, I'd pass it around, but somebody might drop it on their toes and injure themselves. Okay, so this one, actually, we can see mathematically also why it has a long period. Whoops, what did I do?
Microphone. Microphone's in right hand.
That's for saying shit. Okay. We can see mathematically where those long periodicities come from, because in this demonstration, basically, the thing is transparent. You can see through it wherever both wires are transparency. So the transparency is the product of, let's say, the top wire. Okay, so that's the pattern you see, the product of the two transparencies. I can do a Fourier expansion of both of these. Whoops. And I can choose to write it in this way. Let's say there's I'll put a T here for top, a B here for bottom. Transparency is real. So I've just chosen to write it that way. And the two layers are identical, except that one is rotated with respect to the other. So if I have a set of reciprocal lattice vectors, including 0, and I'll just put down here the nearest neighbor reciprocal lattice vectors, one's closest to 0. These are the 4 lattice vectors, reciprocal lattice vectors of one layer, nearest, corresponding to periodicity with x. Let's say these are the same cos x and cos y. And now if I rotate them just a little bit, the other layer has reciprocal lattice vectors at these points. Let me make them x's. So you can see that the longest periods the parts of the transparency squared that vary most slowly in space are when I have two reciprocal lattice vectors from the two layers. Let's call that TB. That are just rotation counterparts of each other. So the difference between these reciprocal lattice vectors is the smallest g minus g primes are these guys. They're basically perpendicular to the direction of the starting reciprocal lattice vector. And you can see the smaller the rotation angle, the smaller this difference in wave vector, the slower this varies in space. So that's what you're seeing. And that is an example of what a moire pattern. And so moire patterns are, it would be, was immediately obvious to people, well, maybe even before this field started, it was obvious that if you have two-dimensional materials, van der Waals materials, very often they end up at a slight twist angle with respect to each other. And then if you look at any property as a function of space, you see this long periodicity coming out, moire periodicity. And if let's say there's something that means that your resolution, the time since you changed your glasses last, if you can't see things that vary rapidly in space, if you have some resolution function that decreases rapidly with the size of momentum, this smallest, longest periodicity will be the only one you see. And so it turns out that nearly that happens in these 2D materials. Go ahead.
You said van der Waals materials. That's in order that the sheets attract and stay in place?
What does this jargon, van der Waals materials, mean? It kind of means, although it's not exactly true, maybe Gene can help me say better, but it kind of means there's no chemical bond between the layer. The layers stick together only because of correlations of the motions in the different sheets.
Correlations of motion or the van der Waals?
Yeah, because, van der Waals interactions is a correlation effect, yeah. So it's not chemical bonds, it's what the chemists call dispersion forces that hold the layers together. Much, much weaker. Their distance between layers is several times of the lattice constant. But it's enough to hold it in place, and it's important that for this being able to get the thing to stick, at some twist angle, that the forces between the layers not be too strong, otherwise they just snap back into alignment.
But you also want it to be translationally invariant.
Yeah. Translationally invariant.
In the plane, the separation between the two.
Yes, or at least periodic. And in fact, it's the separation between the layers is not absolutely constant, but you still get a periodic pattern if the separation between the layers has the periodicity of the moire pattern. If everything is controlled by the local local coordination of the two layers. Okay. Okay. So Lars told me you guys are soft matter physicists, and so soft matter means h bar is 0. So there is, I think, a soft matter problem that connected to these mores that I'm going to dangerously introduce into this talk, which might be sort of understood. I'm not really sure if people are thinking about it. But you might know the right way to think about it immediately. Okay. So, So when I twist those two layers relative to another, in my case, the displacement of one intersection of the wires, which I think of as an atom in one layer, relative to relative to the fixed layer. For a small rotation is just the displacement is perpendicular to the direction from the axis of rotation and proportional to the rotation angle. So if I take that expression, this says the curl of this displacement vector. So this is rigid rotation, okay? And the curl is actually 2 theta, which is a constant. So exactly what happens when these 2 layers are placed on top of each other, the way people prepare twisted bilayers of these van der Waals materials is they take a 2D crystal, cut it in 2, lift up one side that's initially perfectly aligned since it was part of the same crystal, rotate it by a controlled amount, and put it down. And everything depends on what happens when you put it down. So when you put it down, they know macroscopically that the twist angle survives. The twist angle that's measured in the end is always, almost always, I should say, since I don't do experiments myself, smaller than the intended twist angle. So there's some relaxation back. Locally, the energy wants a certain alignment between the 2 layers. It actually wants the atoms of one layer, they're actually honeycomb lattices, and they want AB alignment. So half of the atoms in one layer are in the empty spaces between the atoms in the other layer. And so presumably when the crystal gets put down, it grabs a bunch of places, and there's enough of a constraint, so you're somehow instantaneously, let's say you're instantaneously in a configuration with a constant theta. Then how do you get back, what's the energy landscape? That's what you guys are working on, right? I think it's a very, very pertinent question. People have been concentrating on electronic properties because they're so fascinating, and as you would have guessed already, they involve superconductivity. But there's interesting structural questions here in the statistical mechanics, I think, of the structures that are actually formed. So theta can relax locally, but if you want to change the twist angle, the average theta, over some large distance, you have to move a large number of atoms. And I think that there's experimental information about the energy landscape for twisting back to the twisted state is structurally metastable. There's some landscape of energy barriers that prevent it to get back from AB. And we know experimentally that if you heat up the bilayer enough, it snaps back. And we also know that if you have it stuck in a twisted configuration, it will stay there. Tell me, does it always stay forever? Does it ever accidentally snap back?
If you heat it up, if not, it stays.
And if you heat it up to room temperature?
No, room temperature is stable.
Okay, you have to go above room temperature. Yeah. So, but you can. How much do you have to heat it to make it snap back?
It's a couple of 100 degrees.
Okay. So, yeah.
That's a first order difference.
Well, I think that it's a metastable state. I think there's a collective energy barrier because you cannot relax this twist angle by moving one atom. You have to move a whole bunch of atoms. Yeah. I think the interesting question for me, and maybe this kind of maybe you guys already have an inkling of the answer, is what is the path? What is the path for relaxing this to the stable configuration? But we do know that for experimental timescales, which are weeks. So that means that the collective energy barrier must be, sort of the energy barrier for one atom, which is perhaps a few MeV. times logarithm of, let's say, the experimental time divided by some microscopic time associated with interlayer interactions. So this has got to be at least 15, so there's some EV or so energy barrier, apparently, collective in character, and at least I would like to have a clearer understanding of exactly what is that landscape and how can it be explored experimentally. I think that and what can you say about it theoretically? Okay, so anyway, that was my attempt. Yeah. Okay, so now are these sides of the Blackboard visible for everybody? Okay. So the particular van der Waals superlattice that we're most interested in this week is small twist angle, van der Waals, Moiré superlattices of graphene. And unlike my chicken wire, graphene has a hexagonal crystal with 2 atoms per unit cell. It's actually a honeycomb lattice of carbon atoms. And we know that for even for a simple model of pi electrons hopping around on a honeycomb lattice, then hopping between the A sublattice and the B sublattice creates a splitting between 2 states, bonding and anti-bonding state, that's dependent on momentum. And it turns out that at these points at the corners of the honeycomb lattice for graphene, just by symmetry, these pi orbitals get completely localized on one sublattice or the other. They're degenerate. And at this point, if you look at energy as a function of momentum near these points, this is an isolated graphene. This is energy as a function of momentum measured from the corner of momentum space, corner of the finite momentum space, corner of the Brouin zone. We have 2 crossing pi bands. Those are the only bands we're interested in. And they cross linearly at those points in momentum space. And so what happens to those states when you when you make a Moiré superlattice? So by Moiré superlattice, I mean this long period pattern that you get just by intentionally and in a controlled way twisting one of the 2D layers relative to the other. So most of the interesting behavior I'll talk about in a minute occurs at twist angles of about 1 degree. So that means that there's roughly 300, is that right, pi divided by theta, or 1 over 180, let's say 200 lattice constants. The Moiré period is 200 times longer than the lattice constant of the individual graphene layers. And it turns out that when you twist one layer relative to the other, 2D crystals are not a crystal, and we can't use band structure theory. Okay, and so we don't have our crutch, which is energy as a function of momentum, nearly like free particles. But it turns out there is, in graphene, there is a resolution function for the electron waves and how the 2 layers see each other. First of all, it's these layers at a finite momentum. So these electron waves are not at k equals 0, they're at a finite k. That means the phase of the wave function is varying quite rapidly. It's at the edge of momentum space, and that means there's kind of almost a half wavelength going from one lattice constant to another. Depends a little bit on the direction of momentum. So these are electron waves with a large wave vector. And we're looking at electron tunneling from one layer to the other layer. And the layers, as I mentioned before, are far apart. They're several lattice constants apart. And so that means when electron hops from one layer to another, it can hop easily. There's a similar amplitude for hopping vertically versus hopping to first neighbor vertically, second neighbor vertically, and so on. And because of that, the electron waves are basically taking a Fourier transform when you calculate the tunneling amplitude of how the interlayer tunneling depends on how far you move along. And that means that because of that, any rapid variation produced by the Moire superlattice simply gets filtered out. And all you see, if the only physics you see is to a very good approximation, is a Moire period in the tunneling amplitude from one layer to another. So the tunneling from one layer to another is periodic in space. And if we only have that periodicity, then we can use Bloch's theorem again. So this is, so within this very accurate approximation, it's periodic at every rotation angle. But there's basically a change okay. Slowly, as you move through space, the tunneling from one layer to another changes according to the local configuration, whether the two honeycombs are right on top of each other or in this AB configuration. And so it may be worth mentioning one good way sometimes to think about what's going on in this system in terms of a local electronic structure. The going from A on top of A to A on top of B varies spatially, periodically as you go through the system. And it's well known from, periodic, microscopically periodic configurations like just AA and AB, how the hopping between the layers depends on the coordination. And it turns out, I said a single layer has two states. You can use a representation where the two states are on the two sublattice of the honeycomb, the A sublattice and the B sublattice. So hopping from layer to layer is a 2x2 matrix. When I have two layers and I have a crystalline arrangement, I have four bands. And so it turns out that the band structure changes in a very well understood way as the local coordination changes. And let me just give you a feeling for that by mentioning two extreme cases. So if I have Bernal stacking, that means half of the lattices of one honeycomb are in the middle of the honeycombs of the other. Then it turns out I have a quadratic band crossing. There's no energy gap. If I have A on top of A, the bands look completely different. let's say that's the Fermi energy for neutrality. A on top of A, I have two layers right on top of each other. They just form even and odd states, which are bonding and anti-bonding states. The wave functions have the same dependence on sublattice, and they're either even or odd combinations of the two layers. And then you can see what you do is you get a Fermi surface. Okay? And so go over here. Also turns out that I don't know what I was going to say. Okay. So in the Moiré pattern, we go from places with the band structure on the left there. There are two. It turns out there are two band crossings at the same momentum. The two band crossings of the two layers become degenerate in momentum space here and here, whereas and at these AA points, there's actually a whole ring of points in momentum space where the two bands cross. That's a very singular limit. Everywhere along this line that's the perpendicular divisor of AB to BA, turns out there are 2 points in momentum space, at which you have linear band crossings, and those two linear band crossings, as you go away from this point towards here or here, approach each other and go to zero. So the band structure changes in a complicated way as you go through momentum space. Go ahead.
Is it obvious you don't move the layers slightly laterally to get the registry better and optimize, sort of a Untitled-like effect, optimize the electronic structure by slightly distorting the lattices?
You do slightly distort the lattice, but not very much. And the not very much is, and it's a quantitative effect you can easily take account of that I'm ignoring. And the not very much is because the forces between the layers are, and this is what's special about these materials, the forces between the layers are very weak, and it turns out the bonding within the layers is very strong. So it's very hard to distort the atomic positions. And the other layer doesn't push very hard, but there is a little bit of distortion.
You could then ripple it slightly and then...
And it also does ripple, too.
In registry.
Yeah. But ideally, even this distorted structure is also periodic, and it's that periodicity that we care. The real point is that the energy scales that reflect the fact that the microscopic crystals don't form a lattice, microscopic atomic positions in the two layers, the fact that it doesn't form a lattice, those energy scales are unobservable. Okay, so I'm just going to make one more point, and that is the bingo of all of this. So this is interesting, the electron waves in these Moiré superlattices are, as you can imagine, kind of interesting, and there was a literature connected with them. And it was discovered that at a certain twist angle, which means the Moiré periodicity is connected to a momentum boost when you go from one layer to another. And when the size of the momentum boost, Q, times V, when this energy here is approximately equal to the interlayer tunneling energy, when the layers are strongly coupled together in that sense, then that's when something special happens. And it turns out in that case, the lowest energy bands of what were initially linearly crossing Dirac bands at slightly different momentum, these bands become absolutely flat. That lets nearly absolutely flat. That means strong correlations, as I said at the beginning of the talk. And so this occurs, the number of electrons that fit in these bands is 1 per Moire unit cell. That's 1 for every 10 to the 4th to 10 to the 5th carbon atoms. Okay? But it's also important that there are 2 spin states for every electron. Also, it turns out that instead of having 1 dispersionless band here, you get 2. And there turns out, I said that the crossing low energy states occur at the momentum honeycomb lattice Brouin zone corners, and turns out there are 2 independent of those. So that means instead of 2 internal labels for these flat bands, you have 8. And what was discovered experimentally by Pablo, and we're learning more and more from experimental activity around the world, what was the initial discovery that is now being elaborated on is that number of electrons per Moire. And importantly, this number of electrons is very small. And you can easily electrically, just with electrical gates, go through this entire region of electron density without swapping out any atoms. Okay, and so it turns out that there are band insulators at these points. This is empty band, Moire band. In the Hubbard case, when this band was half filled, there was an insulating state. And here there is also. And it appears as the samples get better and better, insulating states are emerging at all integer numbers of electrons per Moire. And then, bingo! Amazingly, there's superconductivity all throughout this at amazingly high temperatures. The highest temperature in all of nature, I believe, for the ratio of the superconducting critical temperature to the basic underlying electronic energy scale. So it's strong correlation superconductivity. And what certainly I hope, having been disappointed many times in my life, that, with various scientific hopes, that this amazingly tunable experimental system will bring us to a deeper understanding of strong electron correlation superconductivity. So that's why we're all here. So thanks for your attention.
By the way, you said it's much higher temperature than the Kubrick season.
And not really temperature, of course,
No,
but yeah.
Relative to the first.
Yeah.
What is it?
I think that there are some claims, inklings of superconductivity at 5 degrees Kelvin, which is a half of millielectron volt, compared to a bandwidth of, it varies a lot. I don't think we really know what the bandwidth is, but maybe it can be as small as perhaps around 10 millielectron volt.
But if you scale it up through the Kubrick, for example, what would that mean?
I haven't started a company yet, but I'm thinking about it. Oh yeah, easily, yeah. So if this was aluminum, then it would be 1,000 degrees Kelvin, right? Then we could say that we physicists this is the real community that can make the world green.
Aluminum is not the right analogy. That's misleading because aluminum has nothing to do with Fermi temperature. It's electron-photons coupling, right? So that's not the right analogy at all. Cuprate is because electron-electron.
Okay, Mark.
One thing
Yeah.
In your discussion here, there's some small number. which is the distance between the lab spacing and the theta.
Yeah.
Small.
So one thing that has to be small for this, treating the system as periodic.
Well, your
Yeah.
discussion was basically small theta and
Yeah.
separate.
Yeah. Yeah. I think that, yeah. And weak coupling between the layers. You can't do this with anything else. Yeah, it's only van der Waals crystals where you can make these interesting superlattices just by twisting.
Do you get in the regime of tunneling between the two layers or not?
So this, electrons, the flat bands are produced by electron tunneling between the layers. So when people refer to this as, van der Waals crystals, they don't mean there's absolutely no hybridization between the layers. There is some, but it's not the dominant part of what holds it together structurally. So there is some tunneling between the layers.
But it plays a role for the superconducting.
Absolutely. The tunneling between the layers is what produces the strong correlation. Isolated graphene sheets are not strongly correlated. Yeah, it's only that tunneling produces particular spatial dependence of the tunneling amplitude somehow produces these flat bands, which means that the physics is then controlled by interactions and by correlations between different particles. Hi, Sam?
If you were to push down so that the interlayer coupling was stronger, you would just have a different magic angle?
Yeah, that's been done experimentally by Corey. He's at lunch. Yeah, so that's been done. And also...
bandwidth, a similar minimum Fermi energy, things like that?
Similar...
A similar bandwidth?
as far as I know, I'm not sure. It hasn't been looked at by... it has been.
We predicted all that, and Corey actually confirmed it.
Yeah, okay. And, so as long as there's only one twist angle, you can take any graphene multilayer and take some group of layers and twist them, and this kind of stuff will happen. So, for example, one interesting case is where you have 3 layers. Then you can twist the top layer, or you can twist the middle layer. If you twist the middle layer, I think this is kind of interesting from the point of view of superconductivity, because it turns out the middle layer couples to the symmetric combination of the outside layers, right? And it turns out the tunneling is increased by a factor of √2, the hybridization, just because, 1 over √2. But then, so that means the magic angle is √2 times bigger in the case of trilayers, roughly. And but there's also the antisymmetric combination of the outside layers, which is a high velocity band around at the same time, and that might have very interesting superconducting properties. If it superconducts, I don't think we know if it superconducts, but that's an experimental. I think that's a question that can easily be determined.
So for your phase diagram, I imagine that's at this point it's a speculation rather than experiments. I mean,
the phase diagram.
Yeah.
I believe in extrapolating.
Right. So is the implication that all the bands are going flat at the same time? Because I thought that the higher bands are more dispersive.
The bands near neutrality. So in the let me make sure I understand you first. So this is only covering the range of density corresponding to the lowest conduction band and lowest valence band.
So basically the same dispersion, you're not going to the higher bands.
Yeah. So presumably nothing interesting happens in the higher bands. Yeah.
Andre, what at the end of the day determines the width of this flat band? You use the word completely flat, and in theory, is there...
Yeah, so I think we can answer that. I mean, partly, and maybe somebody else can jump in here. But there is a model discovered by Ashvin's group where the bands are a model for which you have perfectly flat bands, where the bandwidth is 0. So that model is physically unrealistic in the sense that there's no hopping between like sublattices. And it seems like it's quite far from a realistic model. But maybe you can still think about doing perturbation away from that. And that's one way of understanding what the width of the band is. So the band, realistic models never have 0 width. But Yeah, they have a width very, very small compared to the energy separation to the next band.
Do you understand the parameter at which smallness happens?
I would say, there is a small parameter is TAA, but it's not really small. Do you know anybody know how to say a better answer to that? Hopping between layers between the same sublattice. In the limit that hopping is 0, the bandwidth goes to 0. That hopping is not small in a physically realistic model, but nevertheless, somehow the way it acts means that it doesn't completely ruin this.
So, Allan, you wrote a paper which just came out saying it's electron-phonon interaction. This is telling me disowning that, is that correct?
No.
No?
Yeah.
But you are.
What?
You wrote a paper recently, a PRL, saying electron-phonon is a BCS electron-phonon superconductivity. Are you disowning that?
Shankar, don't you know how to parse my papers?
My second question is
that's a calculation.
Sure.
What would happen from electron-phonon interactions, and it's a very nice calculation by
that was a joke.
my former. Right. Go ahead.
This is not a joke question, though.
Okay.
The phase diagram that you drew, and the assumption is that insulator is a Mott insulator. How do we know that this is not a Slater insulator? I mean, what evidence in the theoretical experimental is there that is definitely not?
So I'm not one of the people that draws a huge distinction between a Slater insulator and a Mott insulator. We know that these the mean field states that produce gaps have a type of order.
Yeah.
In many cases, we know that order doesn't survive at high temperature, at any finite temperature. Because spin-over coupling is extremely weak in these systems.
Here there is a very high Nil temperature, right? In cuprates.
Yes.
So that's more consistent with a Slater picture, I would say.
That might be. I mean, the cuprates. It's clear that there's a band insulator, right? And I don't care whether you call it Slater or Mott. All I'm trying to say is that here, when I say try to understand the nature of the insulating state, I'm not really talking about whether or not there's long-range order, and maybe that's the distinction you want to draw between the words Mott and Slater.
No, it's chicken and egg. What comes first? Is the antiferromagnetism driving the gap,
or
is Coulomb interaction driving the gap? There is a big distinction.
I don't think so.
You don't?
Yeah, I think it's a qualitative thing that gradually changes.
Oh, that is completely.
Okay, I think we've transitioned.
Yeah.
Okay, thank you, Allan.
Okay, thank you.